This is the first Chapter 5 podcast. I'm going to do the first 3 sections together in one podcast, simply because it's all material that you guys have seen before, and it's just basically going to be a review, so we'll try to get through this as quickly as possible. So this chapter is on projectile motion, not on projectile vomit, and we will actually learn how to predict where that baby's vomit's going to end up landing by the end of the chapter. So the big idea here is that projectile motion can be described by both the horizontal and vertical components of the motion, and that's the way we're going to be able to predict motion. So before we were just looking at simple straight line motion, something moving in a straight line, but now what we're going to do is look at something that's following a curved path like this, such as a baseball being thrown up, and we're going to see that it's a combination of motion horizontally and also motion vertically. So our first section is on vector and scalar quantities, and this is a review, and we're going to remember that a vector quantity has both magnitude and direction. A scalar only has magnitude. So we said that a vector quantity that has magnitude and direction we're going to call a vector, and here's our friend gravity right here, and I'm using the more accurate 9.8 meters per second squared, and I'm also showing its direction down. Velocity is also a vector quantity because it has direction, and as well as acceleration. Acceleration uses velocity, so it has to be a vector. Momentum is also going to be a vector, and we'll talk about that more. Momentum has also to do with velocity, so we're going to talk about that more in the future. Now scalars. Scalar quantity is one that only has magnitude in it, and you can manipulate these just like you do any number, so you can add sand together to make up a concrete mixture. You can add water together or subtract water, which gives you 3 liters in this case, and you can also add minutes onto a trip, so you can manipulate that just as well. So how does a scalar quantity differ from a vector quantity? One word, direction. The vector quantity includes magnitude and direction. Scalar quantity only includes magnitude. So section 5.2, velocity vectors. The result of 2 perpendicular vectors is the diagonal of a rectangle constructed with the 2 vectors as a side. This is also a review. We've done this before. So here what we're going to do is add vectors together, and these are 1 centimeter vectors, and we can see if we add a 1 centimeter vector, which is equal to 20 kilometers per hour, and we add 3 of these together, we're going to end up with 60 kilometers per hour together. 3 centimeter long vector represents 60 kilometers per hour. So let's look at this airplane. When an airplane flies, it's flying through air, and the air itself is also moving. So we have to add those quantities together, and we're talking about, of course, wind. Air that's moving is wind. So if we look at this, look at this one, we have an airplane flying at 80 kilometers per hour, and then we have a wind of 20 kilometers per hour, and as a result we're going to get a total of 100 kilometers per hour. Now let's look at a headwind. If it's airplane's flying 80 and we have a headwind of 20, we're going to end up with a resultant vector of 60 kilometers per hour. So we say that the velocity is often the result of combining 2 or more velocities, and this is just what we talked about here. We talked about the tailwind, and we talked about a headwind when you're with the wind. Now let's consider a crosswind. If we have that same airplane moving at 80 kilometers per hour and there's a wind blowing from west to east, it's going to change the direction of the plane. And what we need to do is, just like we did with the adding a tailwind or subtracting a headwind, we're going to add the 2 vectors together, the airplane's velocity and the crosswind. So what we call this when we add these 2 together is the resultant, and you know that already. And the resultant in this case is going to be a diagonal of a rectangle that we construct with the 2 vectors. This picture right here is amazing if you get a chance to see it. Look for it on YouTube. This is in St. Martin's, and the airport in St. Martin's, literally they land about not even 50 meters from the beach, so the planes fly right down on top of the beach. So here is that example we talked about. We have the 80 kilometer per hour airplane, and it's facing a 60 kilometer per hour crosswind, and as a result, while this is pushing it, while the airplane's traveling this way, the wind is carrying it off to the right, and a resultant, which is what we're talking about, ends up being over here. And with a little help from Pythagorean theorem, we can find that it's 100 kilometers per hour. 80 squared plus 60 squared equals 100 squared. Find the square root of that, we get 100. And here we are again. We're talking about a 3, 4, 5 triangle right here. This is a special version. We know that it's 37 degrees from the horizontal. Anything where we get 3, 4, 5, like a 9, 16, 25, we know we can use this rule. And what if we have a diagonal of a square that is both sides are the same? They're both equal. In that case, our diagonal is going to be the square root of 2 times whatever the sides are, and our angle is going to be 45 degrees. Square root of 2 is also 1.414 if you want to remember that. So, an airplane flying normally at 80 kilometers an hour encounters a wind at a right angle to its forward motion, a crosswind. Will the airplane fly faster or slower than 80 kilometers per hour? And the answer is actually it'll fly faster. It'll increase the speed of the airplane, but it's going to blow it off course. If we have the airplane heading this way, we have wind going that way, the final velocity is going to be in this direction, and while it is bigger, it's off to the side, off course. What is the resultant of two perpendicular vectors? The resultant of two perpendicular vectors is the diagonal of a rectangle constructed with the two vectors as the sides. Section 3. The perpendicular components of a vector are independent of each other. Often, what we'll do is take a single vector, and we're trying to make it into the two component vectors. And we'll put these component vectors at a right angle to each other. So it's gonna, if we have a vector like this, and we want to resolve it into the components, we're going to have one vertical component and one horizontal component. And these two components are at a right angle to each other. So we said that the vector can be resolved into its two components that are at a right angle. And these two vectors are known as the components of the given vector. And this process that we do it with is called resolution. Determining the components of a vector is called resolution. So if you look here, we have a ball here, and the ball is heading in this direction, and we can resolve its components at this point by drawing a rectangle with the components, and on the we have a horizontal component here and a vertical component here. This is not unlike what we did before. So here we go. We can do it with that. What you do is you draw your vector. You draw two axes at a right angle to each other. You draw a dotted line across till you hit the axes, and then where it hits the axes, that's the magnitude of the vector on each of the two axes. Do likewise over here to find your your horizontal component. So how do components of a vector affect each other? The perpendicular components of the vector are actually independent of each other.